Modern enterprise data is a chaotic flood. Rigidly structured spreadsheets, semi-structured files, and massive unstructured media pour into servers every single second. For decades, traditional relational databases utilized a schema-on-write methodology. This required every piece of incoming data to be cleaned, formatted, and forced into a strict structural mold before it could be saved. At enterprise scale, forcing unstructured data through a rigid pipeline creates a massive ingestion bottleneck. The system breaks. The solution is schema on read. Instead of formatting up front, you store raw data exactly as it is, deferring transformation until queried. By decoupling the storage of data from the structuring of data, you eliminate the bottleneck. Deferring transformation to the query stage is the only mathematical way to process massive, unpredictable data streams without paralyzing the system. This centralized schema-on-read repository is called a data lake. And the most resilient framework for building one is Hadoop. Hadoop is frequently categorized as a single database application, but it functions quite differently. It is a distributed, modular ecosystem of open-source tools designed to run across clusters of standard, off-the-shelf commodity hardware. Building this infrastructure correctly requires exact precision. That's why we've partnered with Royal Research to lay out the blueprints for a modern, data-driven enterprise. We will construct the Hadoop ecosystem layer by layer, starting from the physical hardware foundation and working all the way up to the artificial intelligence analytics interface. Relying on a modular network of servers rather than a monolithic supercomputer allows an organization to scale horizontally. When you need more capacity, you simply plug in another server to the existing cluster. The physical baseline of our architecture is the cluster. Dozens, hundreds, or even thousands of basic hardware servers connected together on a network. Over this hardware, we lay the primary logical storage system, the Hadoop Distributed File System, or HDFS. When you ingest a massive file, HDFS doesn't try to squeeze it onto a single hard drive. It fractures that file into smaller, uniform data blocks and scatters them across multiple physical nodes within the cluster. Because commodity hardware will eventually fail, HDFS operates with a native fault tolerance mechanism. It automatically replicates these data blocks across different nodes. If one server dies, the system instantly pulls the backup data from the adjacent node. But distributing raw data across thousands of separate servers introduces a severe logistical problem. How do you manage compute and memory resources across such a decentralized maze? You handle it with Yarn. Yet another resource negotiator is the traffic control layer sitting directly above HDFS. Yarn schedules all the incoming computing jobs and dynamically allocates RAM and CPU power to individual nodes, ensuring the infrastructure operates at maximum efficiency, without overloading any single machine. By pairing the distributed storage of HDFS with the resource management of Yarn, Hadoop weaves cheap, decentralized hardware into a highly resilient, unified storage fabric. Now we have a stable, massive pool of distributed data. The next challenge is executing complex queries across hundreds of independent servers without crashing the network. A traditional data warehouse tries to solve this by moving all the stored data to a central processing unit to run the math. But if you try moving petabytes of data across a network every time you run a query, the network will instantly fail. Hadoop solves this by inverting the compute model entirely, utilizing a core parallel processing engine called MapReduce. Instead of moving the data to the algorithm, the map function takes the algorithm and pushes it directly down into the specific server nodes where the data already lives. The servers perform the calculations locally. Once the local math is complete, the reduced function aggregates those isolated, localized results back up the chain, combining them into a single, cohesive answer for the user. MapReduce ensures extreme scalability because moving a tiny algorithm to the data is always mathematically faster and cheaper than moving petabytes of data. With the storage and compute engines running, we step up to the top architectural layer: how various native data types are actually ingested and queried by end users. Let's look at Pipeline A. This handles structured, highly organized data like SQL tables and spreadsheets. To ingest and read this, we plug in a module called Apache Hive. Hive grants users the ability to run standard, SQL-like queries directly on structured data sitting inside HDFS. Pipeline B handles semi-structured formats like JSON, XML, or CSV files, data with some organizational properties but no strict relational table. We process this pipeline using Apache Pig, a high-level scripting platform designed specifically to map, filter, and organize these semi-structured formats. Pipeline C takes on the heavy lift, completely unstructured data, like raw text logs, audio recordings, and massive video files. For this, Hadoop uses Apache HBase. HBase is a non-relational database module that sits directly on top of HDFS, providing real-time read and write access to massive pools of unstructured data. But there is one final ingestion challenge. Modern enterprises rely on continuous, real-time data streaming from IoT sensors and live social media feeds, which move far too fast for standard batch processing. We bypass the batch delay entirely using modules like Apache Kafka and Apache Flink. These handle near-instantaneous stream processing, analyzing live data for time-sensitive, split-second decisions. This suite of specialized ecosystem tools is the true source of Hadoop's versatility. It allows an enterprise to analyze literally any format of data without forcing it into a unified schema first. The same flexibility that makes schema on read efficient can also lead to organizational chaos. If you continuously ingest millions of files without tracking what they are, your data lake rots into a data swamp. This is an unmanaged dumping ground where information is stored but lacks all context. If your data is undiscoverable, it is useless. A swamp completely neutralizes any attempt to run advanced analytics or train machine learning models because the algorithms simply cannot find clean inputs. Beyond failing at analytics, a swamp creates severe security risks. You cannot audit compliance or enforce access controls on sensitive data if the system itself doesn't know what the data is or where it lives. Raw data storage without a strict organizational framework is not a business asset. It is an expensive, sprawling IT liability. The only antidotes to the data swamp are robust data governance and metadata management. By enforcing strict metadata tagging at the point of ingestion, you explicitly catalog every file that enters the system. This restores discoverability and maps the precise relationships between diverse datasets. Once the metadata maps the system, you can layer on security. Hadoop utilizes Kerberos authentication and modules like Apache Ranger or Sentry to establish strict sector-level access controls, ensuring data remains compliant and protected. This is the ultimate purpose of this massive architecture. A governed data lake provides an unfettered foundation for predictive analytics and artificial intelligence. By combining native format storage, horizontal scaling, and strict metadata governance, a Hadoop data lake built by Royal Research provides a framework for managing storage and processing power alongside the actual growth of the business.